All right, it's 2 p.m. and we're going to go ahead and get started. Want to also say welcome to Southwire Solutions University. We're glad you could come here today. I am Beth Chandler. As I said before, I'm the Training Center Director, or excuse me, the Training Center Coordinator for Southwire Solutions University. And I am coming to you live from the beautiful Carrollton, Georgia. That's also the home of Southwire headquarters. So it's a beautiful day today, and I hope it's a nice day where you're at. This class today is a brand new class for us. It's wire and cable products for renewable markets, wind farms and solar projects. So we're all excited about it because it's brand new. Your presenters today are Casey Spradlin. He's the Chief Applications Engineer, and Erika Akins. She's the Senior Applications Engineer. And we're also excited to have with us Yushin Hawig. She's the Senior Director of Applications Engineering. And we're excited to have everybody with us. So thank you so much. Just a couple of instructions for you. We're going to be muted during the presentation, but we do want you to communicate with us and ask questions. So please type your questions at any time into the chat box. And then Casey, Erika, and Yushin are going to answer those at the end of the presentation. When you are submitting your question, make sure you click on the drop-down menu and select all panelists before you hit enter so we can all see your question. So thank you for that. If there's just one person that's just not sure how to access the chat box, it's very easy. Just at the bottom of your screen, there's a row of icons. You want the one that has the speech bubble on it. It's like almost a round circle. Just left click on that. It's going to turn blue and your chat box is going to pop up on the right-hand side of your screen. And it's also a good idea to pay attention to that. You can go ahead and open it right now because we might be throwing some extra links or information into it for you, and you'll be able to see all those right away. So, all right. I also want to let you know that this course is being recorded, and now we just want to go ahead and get to the content. Don't want to take up any more time, so I'm going to go ahead and throw it over to Casey.
Good afternoon, everyone. Thanks for joining us here. As Beth said, this is a new class for us, both Eric and I. So hopefully, if we make a few errors, we'll correct those next time. So we'll talk about ourselves here for a second. So I've been with Southwire my entire professional career, 17 years in the wire and cable industry. Basically doing application engineering for that time in the utility space for the most part, high voltage underground transmission and medium voltage transmission, 600 volt applications. Part of the ICEA working group. I have a couple of working groups there that I'm the chairman of. So that's the Insulated Conductor Engineers Association. That's a standards body. Chairman of the group of the collaboration between the AEIC and the ICEA, which is known as UPSTAC, which is Utility Power Cable Standards Task Group. So there is, and then I also participate in several IEEE committees. So I will pass it to Erika, and then we'll get started and give her a chance to go ahead.
Good afternoon. I am Erika Akins. I've been with Southwire for 9 years, and my specific focus has been OEM and utility applications and end user support.
All right, thank you, Erika. So we'll move into the presentation here. So I'll speak about this slide for a second, and then Erika will take over. So this is basically what several of the products we're going to be discussing today. Wire and cable products for renewable markets. We're going to be talking about both wind and solar, and a lot of those products overlap, but we'll go through that as we go through the presentation. So you can see here we're going to talk about the wind turbine and tower. So those products, the collection system, and then the substation wiring. We're not going to talk about the transmission lines in this presentation. Erika, I'll let you take this one.
All right. So first we're going to look at the products used in the wind applications. This graphic shows how the wind is captured by the wind turbine to produce electrical power, transforming kinetic energy into electricity. The main focus for this section is going to be on the blade grounding cables, the wind tower cables, and the collection system cables. Next slide. So the first product is DLO, or diesel locomotive cable. It was originally developed for wiring of diesel locomotives, but in wind applications, DLO is used to bring power from the switchgear at the base of the tower to the nacelle. And the nacelle is at the top of the wind tower that houses the gearbox and the generator, connecting the tower and the rotor. DLO can also be used as a flexible motor lead in the nacelle. DLO is an industry name for the cable. It's actually listed as RHH RHW-2 per UL 44 and RW90 per CSA C22.2 number 38. In 2015, UL created a subject for heavy-duty flexible power cables to address the DLO construction, specifically the KC mill sizes, because those weren't addressed in UL 44. CSA does have a type DLO product, but for the most part, in the U.S., the product that we see for DLO is RHH, RHW-2, RW90, and then the heavy-duty flexible power cable. Next slide. DLO is a very flexible cable to allow for constant torsion. Typically, it's going to be a 10 copper conductor, but there are bare copper constructions. It's Class I strand. It's a 2-layer composite insulation of EPR and CPE. It's going to be 90 degrees C wet or dry. It's a 2 kV product. There are a number of flame ratings that are on this product, FT4, VW1, and then CT for 1/aught and larger sizes. It's typically insulated, sunlight resistant, oil resistant, and then the size ranges are 10 gauge to 1,101.1 KC mil, where the KC mil sizes are not your standard KC mil sizes that you would see in ASTM or UL 44. Next slide. So there is a aluminum version of the DLO with the compact aluminum strand. This is mostly for non-torsion, non-flexing applications to help reduce the cost where a non-flexing cable can be used. It carries the same ratings as the 10 copper construction. It just doesn't carry the heavy-duty flexible power cable rating. And the KC mil sizes are going to be your standard KC mil sizes seen in ASTM and UL 44. There are a number of different vertical flame ratings that are standard on most of the DLO products in the market. With the product being installed vertically, it's critical that the flame will self-extinguish and not propagate the length of the product. And so the first flame rating that we can look at is the VW1. The flame is similar to a Bunsen burner. It is applied at 20 degrees angle on a 2-foot sample. This flame is applied in 5 cycles, so it's 15 seconds on, 15 seconds off, for a maximum of 60 seconds. And then there's 3 different failure modes, with one being that it continues to burn after 60 seconds after the flame is removed. And then the other failure mode is the paper at the top of the apparatus being charred more than 25%, or either the cotton at the bottom is ignited. Next slide. The FT4 flame rating is more stringent of a test. The flame is 70,000 BTU per hour. The cables are secured in a vertical ladder with the quantity depending on the diameter of the cable. The sample is 8 foot, and then the flame is applied at a 20-degree angle for 20 minutes, and 2 tests would be performed. The failure mode is the area of the damage must be less than 1.5 meters. For the 1/0 and larger sizes, there's the CT rating for use in cable trays. It's fairly similar to the FT4 flame test, with the exception that the flame does not have to be at 20-degree angle. And then the failure mode is different in the sense that it just has to be less than the entire length of the sample. Another product that we see in the wind turbine is the wind turbine tray cable. It's designed for flexing applications to withstand torsion. It's used as control cables in the NAND cell. It can be used for interconnecting sensors in the down tower as a power cable. The construction of the cable is governed by UL Subject 2277. The construction of wind turbine tray cables is the same as UL tray cables, except it's not allowed to be marked -ER for exposed, run, or direct buried. So in the industry, you'll see that it's often dual rated with tray cables, since those ratings are not for the wind turbine tray cable. The conductors are typically copper or tin copper, a very flexible strand, something like Class K. It can be from 18 gauge to 2000 kc mil. There are a number of different common insulations that we see is XLP or PVC nylon or PVC, and depending on what your inner conductors are rated is going to determine the temperature of the entire product. So if you have XHHW-2 inner conductors, then it's going to be a 90C wet or dry cable. The low temperature rating on this product is 40 degrees C, and that would be for the cold bend and cold impact. It's typically a 1,000-volt rating where the jacket is either PVC or TPE, but more commonly TPE, just because of the low temperature characteristics of the material.
All right. Thank you, Erika. I'll throw up this slide, just a reminder of where we're going here. So we're going to move to the collection system here, and I'll talk about the B voltage cables and the bare copper. So the uses for the medium voltage cables would be, and these would fall under the UL 1072 ratings, and either MB90 or MB105, depending on how they're operated. So this runs from the turbine to turbine transformer back to the grid. So as you can see here, the construction on the left here, the construction is usually polymeric insulated. So that's some type of plastic. And then it's a shielded cable and jacketed on top of the shield. So the conductors are typically aluminum, as seen here, Copper is an option, just like any other medium voltage. It does come at a premium price or whatever. So that's usually why aluminum is chosen. So the size ranges from pretty small number 2 gauge to up to 2,000 kcmil typically, and it's larger if needed. But that's for medium voltage accessories. You're probably not going to find any larger than 2,000 kcmil. Temperature rating is 90 or 105. It's typically 105. In these applications, that gives more ampacity for the circuit, for the cable chosen. The insulation type is typically tree retardant cross-linked polyethylene, or TRX-LPE, and EPR, both leaded and non-leaded, is also an option. As the metallic shield is going to be typically a concentric neutral type shield, and but tape, a helical applied tape or longitudinally corrugated tape is an option, and that's what's here on the left here. This would be your helically applied tape on the far left, and in the center would be your longitudinally corrugated tape shield. As we said, the concentric neutral here on the right is generally the most widely used option. And we will, in the next slides, I will talk about the shield rating and what's different about what's most widely used in wind farm applications, or renewable applications, I should say. Jackets are typically cross-linked polyethylene, which is a little bit different, and we'll talk about that in some future slides. In the utility space, they're usually using a linear low-density polyethylene, or PVC, in the industrial applications, but for renewable applications, it's typically going to be the cross-linked version of those, cross-linked version of polyethylene. Voltage rating, just like any medium voltage, it can be from 5 to 46 kV, but we typically see that most renewable applications have settled in on a 35 kV voltage range. And again, as I mentioned at the beginning, the ratings, UL 1072 could be either MV90 or MV105 under that rating, under that UL designation. Typically, we're seeing these being used at MV105, which that is the 105 degrees C operating temperature for the conductor. So we'll talk about the differences in the jacket for renewable applications. So this is both for wind farm and solar applications. So LLDPE is linear low density polyethylene, which is a thermoplastic jacket type. So normally these are used on cables that have a conductor temperature of max conductor temperature of 90 degrees C, and so therefore once the dissipation of the temperature goes through the different layers of the cable, is typically you're not going to have to see more than 75. That limits that jacket temperature to 75 degrees C. And it will be something lower than that in the 60 range, most likely when you have a fully 100% operated cable at 90 degrees C conductor temperature. So what we're seeing in wind farms is a thermoset jacket. So we, just like the insulation system, we are cross-linking the jacket. Although there's a different process, you're not doing it in a curing tube. It's typically a moisture cure application, or ambient cure application, so it cures due to the moisture in the air after extrusion. So that allows the conductor temperature, that allows the jacket temperature to be higher, so therefore you can operate the conductor temperature higher as well, so that you operate the conductor up to 105, and then your jacket temperature has a maximum rating of 90. And again, you'd be somewhere in the 80 degree range, 80 degrees C range, operating on the jacket. So ICA has different testing for both of these types of jackets. So in the factory, before it leaves the manufacturing process, before it leaves the manufacturer, we're going to test it a couple differently. So for the thermoplastic jacket, you're going to have the air oven aging. You're going to do tensile elongation on the unaged, and then you're going to age it for 48 hours at 100 degrees C, and then you're going to, that has another tensile elongation criteria. And so for the thermoset jacket, there is a higher, obviously, you're going to age it at a higher temperature because it is a different, the cross-linking process allows it to operate at a higher temperature. So you're going to test that. And so you're actually going to test it at 121 degrees C for 168 hours. The heat deformation or heat distortion test, sometimes you'll hear it named both. So that is where you take, put a weight you put the specimen in an oven for a certain amount of time, and then you put a weight on it, and you check that there's a percentage difference there. So here, the temperature on the thermoplastic is 100, and the temperature on the thermoset is 131. And the percent deformation, or how much the weight presses down on the sample, is 30%, allows up to 30% deformation. And for thermoset, CSA and UL have a little bit different criteria. One is 30 and one is 50. So that's they're just a little bit different in the standards there. For thermoplastic, there's some other types of thermoplastic jackets, those being listed here. So you got high density polyethylene, which is a little bit more robust than linear low density polyethylene. You got polypropylene, similar to high density polyethylene. It's just a tougher jacket material. And then you've got CPE, which is chlorinated polyethylene, and PVC, which I'm sure you most know, polyvinyl chloride. On the thermoset side, you've got some low smoke zero halogen options, and you've got the cross-link polyolefin option, and then CPE thermoset. So just like on your thermoplastic, you have a thermoset or cross-linked version. So just to reiterate the differences between what's cross-linked and what it means to be cross-linked. So you have your polymer chains here under the thermoplastic in the center. You see all your polymer chains are in line with each other and they're not connected. So therefore, this jacket can melt and flow once it gets up to a certain temperature, like a candle. Here on your thermoset jacket, you see how once you cross-link it, you're actually taking the polymer chains and linking them together, and therefore they will never change their shape. They might, under a certain temperature, they will disintegrate and char, but they'll never melt and flow. So we'll talk about the short circuit characteristics of these wind farm and solar applications, operating them at a higher conductor temperature to squeeze all the ampacity that they can out of the thermoplastic or thermoset insulation, I should say. They also, the engineers here and the developers also want to squeeze all the short circuit carrying capacity out of the concentric neutrals that they can. So that comes along with the thermoset jacket or the cross-link jacket, in that allows you to operate the short circuit current at a higher temperature. So that allows you to operate the neutrals at a higher temperature. So therefore, you can it provides additional short circuit current. Well, if there's only so much needed, you can actually take advantage of that and reduce. Instead of having like a 1/3 neutral, you could have like a 1/4 neutral, and that would help you there with some of the cost and weight savings of the cable. So to do that, we're showing you here the calculation of the short circuit current, and you can see here the T2 and T1 are highlighted on the right here in this brown box. And so you can I'll show you on the next slide here how those T2 and T1 change according to how you're operating your cable. So the T1, this is all governed by the ICA standard. This is P45482, which I'm actually the chairman of. So the 105 here, if you're going to operate the conductor at 105 and say for 35 kV cable, your T1 would be 95. And if you're going to operate, say, an MV90 cable for that same 35 kV thickness, this would be your insulation thickness at that. It's not based on voltage, it's based on thickness. So your T1 would be 80, and you would use that in your calculation. So for T2, we're going to have a cross-link jacket or thermoset. So that allows you to use 350 for T2. And then obviously the difference there would be if you're going to use the low density polyethylene that I talked about, then that would limit you to 200 degrees C. So you can see the difference there. Go back here, you have a lower T1, which helps you for your 90 degrees C, but you have also a lower T2. So your overall current would be lower. And then going back to the 105, you're going to have a higher T1, but you have a significantly higher T2, so that allows you to achieve a higher short circuit carrying capacity for the same neutrals. Just to give you an example of that, here's a quick example, wind farm example. So a 1-aught-19 35 kV with 345 mils of TRXLP insulation. So an MV90 cable is going to have that thermoplastic polyethylene jacket. And then so a new standard 1/3 neutral would be like a 6x14 gauge, 6 number 14s. And then so you can see here reduced neutral. This is what is referred to as commonly having an XLP jacket. You're going to have a reduced neutral, so roughly a fourth, like I said, and that's about 7 number 16s. So you can see here the reduction, about a 27% reduction in total neutral area, copper neutral area. So that saves you on both cost, and you can see here it's about a 6% savings in weight, all while delivering the same short circuit performance of 2.2 Ka for 30 cycles. So here, just 5 to 15% depending on cost savings, depending on how much neutrals are reduced. So the next, I throw the slide up again to show you where we're going. We're going to talk about the bare copper next. So bare copper is used in the collection system and inside the substation, obviously. So we'll go back here to the side, the collection system, which I guess we'd have to go all the way back to the first one. So we'll move along to save time. But the construction is either solid or aluminum. And I have a few examples here. The conductors can be bare, obviously, which most of the time they are. Tinned, just to kind of, sometimes there's some theft deterrent solutions made, and we'll talk about one of the Southwire's innovative theft deterrent systems coming up. But anyway, tinned is an option, and then copper clad steel. So those are sometimes used as theft deterrent. So Southwire has an innovative product that they've come up with called Proof Positive, and I'll talk about that in the next slide. So the size ranges are from number 6 gauge to up to 500 kc mil typically, and obviously we're talking about bare copper, so it's not going to have any kind of jacket. Sometimes in certain applications we have customers that are covering their copper ground wires just solely based off of copper theft, trying to mitigate copper theft issues. So Proof Positive, Southwire has this traceable theft deterrent Proof Positive copper and Proof Positive copper clad steel. So this is to help the utilities protect their investment. Everybody knows that once upon a time, when the economy was pretty low, there was quite a bit of copper theft going on. May or may not still be going on at those same levels, but we'd like to think that Southwire's innovative product has helped mitigate some of that. So here we have, take your standard copper, bare stranded, and we tin coat one of the layers, And then on the center strand, we actually place a license code and a serial number for every, it's traceable by every foot of cable. So now that you have identification, and these serial numbers are placed on a website, and those are assigned to the customer when they purchase the proof positive, the real tag, all that's gone through a website or whatnot, and they can go to the website and log on and take ownership of that cable. And so if it ever shows up in a court case, the utility or the wind farm or the IOU or whatever has proof that cable was there, so they can prosecute. So you see here, identification-wise, we put a 10 outer layer, outer strand, so that the scrap yards can identify that, hey, this is a proof positive product, and we've had good success with that, with limiting with the education, after the education of the scrap yards. So that has helped reduce the problem as well. So also another deterrent is this copper-clad steel. The steel core in the middle is hardened steel, so that is a little bit harder to cut. So that's also one of the attributes of this product. So we'll move to solar projects now. A lot of these are the same, but there are some differences, and I'll let Erika take back over here on this slide.
All right, so moving into solar projects and applications, at a high level, the solar panels collect the sunlight to make DC power. The inverter converts the DC power to AC power, and then you have the transformers that will step up the voltage to either substation voltages or the grid. And then you have a tracking system that uses power and control to allow the panels to follow the sun. And so the products that we're going to look at that are involved in that process are going to be PV wire, medium voltage cables, and then cable and conduit. Next slide. So for photovoltaic or PV wire, these cables are part of the collection cables. They are cables, part of the system that collects the cable off of the panels and takes it to be used elsewhere. This portion of the farm was historically put in trenches, but we're seeing more and more of those cables being installed above ground in cabling systems. PV wire can be used for interconnection between the solar panels and between the combiner boxes and the inverter. And then for OEM applications, you'll see PV wire being used as kits or pigtails for the modules. It's governed by UL 4703, which is not harmonized at this point with CSA C22.2 number 271. PV wire can be copper or aluminum. The aluminum conductors are the 8000 series aluminum alloy because it's often dual rated with RHW-2, and UL 4703 makes many references back to UL 44. The conductors can range from 18 gauge to 2000 kc mil for copper, and then 12 gauge to 2000 kc mil for the aluminum constructions. Typically, it's going to be an XLP insulation, but there is, the standard does allow for composite insulation, like an EPR CPE construction. It's typically going to be 2000 volts, but there is a 600 volt option. It's going to be 90 degrees C, wet or dry, -40, cold thin, cold impact. It's going to be sunlight resistant and direct burial. And the sunlight resistance doesn't mean that it's going to be color fast. It just means that the insulation properties will be retained. So like your tensile elongation will be retained after UV exposure. There will be some color fading of the insulation, but it's more of a cosmetic issue than it is an indicator of the quality of the insulation. For the flame rating, it's going to be VW1, and for the 1/0 and larger sizes, it'll be CP rated for use in cable trays. Next slide. CSA has two different constructions for PV wire, RPVU90 and RPV90, but the more common product is the RPVU90 because the U means that it can be direct buried for underground, and then the 90 is for the temperature rating. These conductors can be copper or aluminum as well, and the aluminum is going to be the 8000 series aluminum, 18 gauge to 2000 kcmil for copper, and then 12 gauge to 2000 kcmil for aluminum. It can be made with XLP or EPR CPE insulation. The product can be rated for 1 kV or 2 kV. It's 90 C wet or dry. It has a low temperature of -40 C for the cold impact and cold bend. It's going to be sunlight resistant and direct buried. This particular product is going to have an FT1 flame rating, which is very similar to the VW1 test. There's just a little bit difference in the cycling of the flame and the failure mode. If you're looking for a more flexible conductor for tin copper and copper construction, there are other stranding options available. Typically, it's going to be a Class B strand, but Class C and Class K are available. With the increase in the number of strands, will give you a little bit better flexibility of the product. And so, for example, a 10 gauge Class B is going to have 7 strands versus Class C, which has 19, versus Class K, which has 105 strands. And as I mentioned earlier, UL and CSA are not harmonized. There are differences in the thickness of insulation for each of the constructions. So for RPV90, those insulation thicknesses are going to be the same as RW90. And then for RPVU90, it's going to have the same thicknesses as an RWU90. And in the table below just gives a reference for the thickness of the single layer insulation level, where the PV wire 2 kV construction is a little bit thicker when you're looking at the smaller sizes, but then when you get to 1000 kcmil, the RPVU is going to have more insulation. And so that's just a little table to show why the RPV wire would not be dual rated for UL and CSA.
Okay, thank you, Erica. So I'll throw this back up to talk about, I'll close this out here talking again about the medium voltage used in solar projects and also cable and conduit, which can be used throughout the project. So the medium voltage cable used for solar farms is much the same as in the wind farm applications that we've already discussed. So basically, this is the same slide in that, except for where really nothing. So, we'll move along and talk about the 105 degree C rating and what challenges that might present in the future, long term. So there two types. So medium voltage at 105, typically this was reserved, you might have thought this was reserved for EPR type installations. In the recent years, last 5 years or so, TRXLP also has been used at this temperature. So there is some considerations for using this for TRXLP at this temperature, though. You need to confirm that your accessory manufacturers can't accept that that their components operate long term at these temperatures with TRXLP cables, and then with the increased current and with the increased temperature, also gives you an increased current, which is going to reduce your losses or provide you greater losses and reduce your system efficiency. Higher operating temperatures can dry out the soil and the surrounding cable, so that could increase the soil thermal resistivity, therefore leading to possible thermal runaway. So that's a consideration to think about. Number 4 there, the increased operating temperature slightly decreases the metallic shield short circuit current rating. So we showed you that with the different temperatures of the T1 values that we talked about in the previous, in talking about wind farms. So Nigel, I believe you had a comment about in your in the chat box about the long-term validity of the cable when you're going to reduce the neutral and worrying about the deterioration of the concentric neutrals. So my advice is to wait for it. I know Nigel personally, so I'm just giving him a hard time. So if that is a concern for you, then there are additional options that we can add to the cable, and one of those is a moisture blocking powder or more water soluble tape under the jacket that will prevent moisture from wicking up and down the cable, and also help slow any effects that moisture might have on deterioration of the copper neutral, or i.e. corrosion. So this is either done, as I said, by a water blocking powder or a water soluble tape, and the water soluble tape just contains the water blocking powder. The other option is just to dust the cable when you're applying, right before you apply the jacket, you dust the water blocking powder onto the cable, and then you seal it in with the jacket. So this water absorbing super absorbent powder swells from 400 to 600 times its own volume, and therefore it will limit the water droplets that might penetrate the jacket over time. It will not let them travel up and down the cable. So this super absorbent powder is also can be used in the conductor to limit with a combination of a compound that limits a pumpable compound, I should add, that's during the production of the conductor. You pump this compound in, and then you dust that compound with this super absorbent powder that we talked about, and that combination will prevent, it's called a moisture block conductor, so therefore that will prevent any moisture from traveling up and down the cable in the event that the conductor is exposed, either via a termination leaking or splice leaking, or in the event you have a failure in a direct bearing system, and you want to splice the failure point right there and keep the remaining cable. You don't have to worry about any moisture getting inside the conductor and causing any long-term damage. So you can see here on the left, the picture shows that the strand fill, each of these interstices, that's the word for the day, that is the gaps in between the strands. Those are normally filled with air, and that would be filled with this pumpable compound and moisture block compound, and that would seal the conductor up. And then as you see here, it's a black compound. It's a carbon black because it's semiconductive, obviously. So moving on to cable and conduit, these can be used anywhere with any types of cable. Southwire, we personally make these cables these conduits in-house, and we extrude the conduit around the cable. And the conduit has a lubricant is pre-lubed, so that in the event that you ever need to pull the cable out, there is lubrication there to help with that. So can be used for medium voltage cables. 15 to 35 kV is our limitation here due to the size and the weight, typically up to 1250 kc mil. PV wire can be installed in conduit. Airport lighting cable. The PV and the MV cables are obviously pertinent to the conversation here about renewables, but just on the other hand, we can put airport lighting cable, 600 volt UD, low voltage fiber optics, and even building wire. So that's just a lot of the materials that we frequently put in CIC. So the benefits of CIC, so it's a high-density polyethylene conduit. As I said, we extrude it at our facility in Carrollton, Georgia. And so the high density is a lot more flexible than the PVC, available in various colors and are the stripes of different colors, stripes or no stripes. We can put multiple cables in a conduit. So the cables are pre-installed and they move freely. There protects the cable. And then we have all the standard ASTM and UL thicknesses. And so that we have the 40 and the 80 thicknesses as far as and then we have the I believe it's forget the other standard. My train of thought just left there. So allows for various installation methods. So these come on, you see here, there's a picture of the reel, very lightweight reel that obviously is designed to hold the weight, but they break down and they're easily transported back to us. So it helps reduce freight costs because of the lighter reel there. Reduces labor costs because you're pulling in the cable and the conduit at one time. You don't have the different crews on site doing two different jobs. And then can reduce replacement and upgrades costs because you can leave the conduit in the ground and pull the cable out and put in a upgraded larger conductor cable or whatnot. So here's some of the applicable standards: UL, ASTM, NEMA, and then there's some NEC articles that pertain to these CIC. And then all of our cables will be designed to meet the NEC minimum fill rates. That's part of our design. So with that, that's the end of our presentation. I see we've got several questions. I believe Houston might have been answering some of these. And so, Houston, if you want to throw any of these at us that you haven't answered, then I'll let me know, because I think I answered one that you had already answered before. So we thank you for your time, and I'll just final plug. If you have any questions or comments, this cable tech support at southwire.com will reach both Erika and I if you have any additional questions or if you have any additional application questions about Southwire products.
Casey, I had a question, I think, that y'all didn't answer, I think. Can you tell me if you answered, what is the main differences, or what are the main differences between PV wire and RPVU? Did you answer that one?
And some of these we may not be able to answer today, but we'll certainly get back to you. And Erika, I'll let you take that one or punt it, whichever.
Yeah, so the main difference between the PV wire and RPVU are going to be the thicknesses in the insulation. Most of the product is going to have the same optional ratings and things of that nature. That would be the only difference that I'm aware of.
Okay, thank you. Yushin, did you have anything?
Yes, I think we have a question related to the jacket options. Questions on HDPE, which is high density polyethylene, and the differences between HDPE and LLDPE, which stands for linear low density polyethylene. So I have answered a few questions. Yes, we can make any MV cables with HDPE jacket, which is tougher, harder, and more abuse resistant, and LLDPE is more flexible. And the question is for exposure to high humidity, which one will be better? So high density polyethylene, because of the higher molecular weight, that's why it has a higher density. So in terms of humidity, there is an ASTM test method. It's called moisture vapor transmission rate test method. So HDPE will have a lower vapor transmission rate compared to its counterpart, which is LLDPE or LDPE. So if you have concerned with high humidity exposure, I will say high density polyethylene or cross-linked polyethylene, which is, again, thermoset. So the moisture vapor transmission rate for HDPE or XOPE will be much lower than that of thermoplastic linear low density polyethylene. And another question, I think this is still related to the jacketing compound. Do we have a flame test result or passing flame tests for those compounds? So the answer is no. For all the polyolefin type of polymer family, which is polyethylene-based polypropylene, LLDPE, high-density polyethylene, or cross-linked polyethylene, those polyolefin-based jacketing compound, they do not have any flame retardant additive. So they do not meet any of the UL or CSA flame test. So if you're looking for a flame retardant jacketing material, we have low smoke zero halogen. We also have FR flame retardant PVC jacket. So thank you for the question. I think that's all. And we will, there are a few questions that came in through the internal Southwire people. We will take that offline. So I think that's it.
I have one final comment on the proof positive, Yushin. Evidently, I didn't do a good job here on explaining this. So the center strand has the identification. It is etched into the center strand, which in the center strand is obviously tinned so the etching comes up, and it's copper-clad steel, I should say, so that and then the etching has the serial numbers and the information there. And Yushin, you attached a link to our website where they can find more information too. So again, we thank you everyone for your participation in our webinar. We do have, I think Beth has placed a link to more webinars from Southwire, from people like me and Erika that and some of our colleagues. So and several other products at Southwire. So Beth, I'll let you talk about that if you would like.
Yeah, I will just say, just if y'all want to click on that link that I put in there, and you can find all of our classes. We look forward to seeing you guys next time. We really appreciate you all joining us today, and especially we appreciate Casey and Erika for being here, and also for Yushin. Y'all did a great job. Thank y'all so much. And with that, I'll just go ahead and end it. There's lots of thanks in the chat box. Thanks for y'all to everyone listening that attended, the audience. Thank y'all very much for showing up. We appreciate it. All right, we'll see you guys next time. All right, bye-bye.
Yeah.